Hello, everyone. I'm glad to be here for our lab on aliasing phenomena in continuation to downsampling and sampling in your digital signal processing course. Today, first, we will have an intuition what actually aliasing is and have a better feeling what it is actually. And we will go through a more formal definition, and we would present the solution to aliasing issue with an example, and finally we will summarize our class. So to give you an intuition, first I would like to describe and give you a case scenario. Just imagine you are working in somewhere, and you go there to work in some number of working days, right? We have 5 working days, and if you go and work there 5 times a week during 5 working days, now if you consider how many times your supervisor comes and checks if you are actually working, so if your supervisor comes to check how many times you have worked there 3 times a week, which is maybe 3 working days, he would just see you are working 3 times a week. But he would have the ambiguous idea, maybe you are working with 4 times a week frequency, with 5 times a week frequency, or maybe just 3 times a week frequency. This is the ambiguous idea. So this is the problem raised when we have a lower sampling rate, the number of times that your supervisor comes to the office to check if you are working. Lower sampling rate than the number of times that you actually work. So this is the intuition behind. In real world, we have more complex than a discrete low frequency case example of working in an office. We probably face with sensors, which are more likely to be continuous. And since we are computer scientists, we will sample these sensors, so we will have a digital view of what actually data are in a more, let's say, in a more discrete format. So if now let's consider the case. We have the sampling frequency of 5. Let's see how would it change if actually the frequency of the signal change. So first you go through lower frequencies. For example, in 0.63 hertz, 0.63, we would actually have this is actually 63 hertz because our continuous rate of sampling is 100 hertz, so we are expecting 63 hertz. And if we have sampling of 500 hertz, what we would see, we'll expect enough number of sampling, which could give us an idea of what the actual signal is. And if we increase our frequency, we will have less number of samples for each cycle. And by increasing the range closer and closer to the sampling frequency, we will have less and less number of samples per each cycle. But once we pass the half of this frequency range from 2.5 and above, you start to see a new thing, maybe more to be more specific, what we call aliasing phenomena. That we don't actually see that the output signal after sampling would actually be a bit shifted from the input signal with no actual collision no actual alignment between them. So, and if we look at the frequency domain, we will see we have another new range of frequencies after sampling. Meanwhile, our input has different range of frequencies, right? And ultimately, if we indeed have farther, more bigger frequencies closer to the sampling, we will have much wider range, a wider gap between the frequency domain candidates. So, and ultimately, when we have indeed the same frequency signal as our sampling range. This is what we actually see. So this is we all after sampling we see zero frequency in our range. So this is what actually happens. So well, you might got a bit confused by our example, but we will go through a more interesting demonstration of what I've just told you. So by definition, aliasing arises when we have two different frequencies, and when we have a sequence of sine wave samples, and we are sampling this samples with frequency f1 and f0, then we would have ambiguous samples which would map to the same sampling point. So this is exactly where the aliasing happens. Now, more formally, if we represent our sampling range with frequency f0 as this x1n series, which is sine of 2 pi f0, and n would be our series index over the sampling frequency. Now, if we have if we just add if we want to present f1 as the sampling candidate, then as we had before, f1 is basically f0 plus f sampling frequency, right? So the representative for our f1 series would be 2 pi f0 plus fs times n over fs. So what would happen if we just decompose this inner parentheses, we would have 2 pi f0 n over fs plus 2 pi n. And since sine is a periodic function, 2 pi n would be canceled out. So what we would actually have is 2 pi f0 n over fs, which is again the same representative for f0 series sampling. So we would have two same samples for two different frequencies. And if we go below this frequency range, if we go actually below this with f0 below the sampling frequency, we would have again the same candidate with a negative mark, since sine is a odd function. So we will for the negative part of the story, we will have minus the x1 series candidate for sampling. So basically what this means is we would have aliasing frequencies within the range of minus our sampling frequency and plus the sampling frequency. So basically this is trying to tell us whenever we are trying to sample a signal with frequency f, we must make sure our sampling frequency is more than double of the signal frequency. Let's go through a case example to make this experience a bit more fun and understanding. I got a voice clip, and this is the amplitude range. This sample was this sound clip was sampled at frequency of 44.1 kilohertz. This is how it sounds like. I hope you liked it. Let's check the frequency spectrum of this sample. As you see, we have a range of frequencies between -20 to +20 kilohertz. So now let's reduce the sampling rate by a factor of 3, and let's see what actually changed. So we just dropped the frame rate to the factor of 3. This way we would have the range of frequencies with less than the spectrum that we had. It was about between the range of -20 to +20 kilohertz. By dividing 44 by 3, we will have a smaller interval of frequencies. So before sampling, for such a case, we need a basically a filter to get rid of all the aliased frequencies, and this is what is actually called anti-aliasing filter. Anti-aliasing filter is basically a low pass filter within the range of the cutoff that we have, which is less than the sampling frequency or more than the double of the sampling frequency. So let's check out our so this sample is simulating the sampling process, and basically we just get the values of the previous sample with whatever sample rate, and we divide it by the number of factor. Basically, we hop every 3 samples. We just drop the 2 other samples, and the rest of it is 0. And so let's see what happens after we make such a downsampling. And so you basically hear more of a corrupted noises within your samples, maybe more low frequency and very, very high frequency noises within the original sound that we actually heard with higher sampling rate. And if we show the spectrum, we see some aliased frequency within this range, exactly right after our sampling frequency spectrum. So we need to get rid of these 2 extra frequency ranges, and we would apply an anti-aliasing filter, which is basically a low-pass filter over the out-of-bound frequencies. And after we get rid of the extra frequencies that appeared in the result of our downsampling, we have less actual energy, or maybe less power in the sampling. Of course, we lost all those peaks before we had, but we still will be able to see what actual data represents. So now let's check the difference between the downsampled and the sample signal, and you see we have a very small difference in the sense of the signal difference. We can convert after we do our filtering, we can convert from frequency domain back to amplitude domain. And now we can hear how does our anti-aliased video sound clip downsample sound like. So we have a small difference between the interpolated wave and the filtered wave, as we have already checked. So one more time, we will end this slide, end this lab with our summary. Basically, aliasing occurs when we are downsampling a signal or sampling a signal with a higher frequency than our sampling frequency. And the aliasing comes when the name itself means we have an ambiguous sample which was mapped to another frequency which it does not belong to due to our low number of sampling per unit of time. This issue can be tackled by applying a low-pass filter through the frequencies out of our sampling frequency, which was aliased. And in audio, aliasing can have different sounds depending on where actually the signals originate from. So thanks for your attention. Have a good day.